Okay, well, here we go on we're sections 12.1, 12.2, and 12.3 now. This is some other types of organic compounds: alcohols, thiols, ethers, aldehydes, and ketones. And they start off with a thing on skin cancer and this actually is about sunscreen later on. They talk about some of the compounds. If you go all the way to page 421 of your text, the end of the chapter, you're going to find the resolution of this, or the finale or the conclusion of this story about the dermatology nurse. They talk about using sunscreens, and a lot of sunscreens are actually, I'm going to go ahead and take a look at page 421 if you want to take a look at it or make a note of it. They give you some examples here of sunscreens. Let me get this thing open. These pages don't want to separate. Here we go. There's actually most compounds that are used medicinally for foods and so forth have a lot of the functional groups that we've talked about. And sunscreens are, I see one here that's, it's a ketone, it's an aromatic compound, it's an ether, it's a phenol, all at the same time. And these things have aldehydes and ketones in this particular context, but these things have all kinds of properties that when they're strung together, an aromatic and a ketone, and maybe throw the phenolic group on the aromatic ring, you're going to start seeing it's going to affect how these things absorb light. It'll start absorbing ultraviolet light at fairly low wavelength ultraviolet, which you think, well, low wavelength ultraviolet, well, that's not going to hurt me, right? It's the high wavelengths, the high energy, low frequency, I just caught myself, low frequency ultraviolet. You say, well, that's not going to hurt me. It's the high frequency, the higher energy that's going to hurt. Well, actually, the real high frequency stuff really doesn't get through the atmosphere. It's the stuff that's just on the other side of the ultraviolet spectrum. Actually, they're all bad, but these things will absorb light right in the region where it's going to. There's the sun, there's the tanning rays, and they can do some damage as well. And the sunscreens absorb these things, but they're good for you to use. You can still. I know people like to get suntans, but these things, it is good to use sunscreens, and a lot of them have these functional groups. Okay, so we're going to go through alcohols, phenols, thiols, and ethers. They're all pretty similar. They are, an alcohol contains a hydroxyl group. That's it. You see methanol is there, phenol. Well, phenol is a phenol because it has a hydroxyl group bonded to a benzene ring. So it's an aromatic alcohol. You can look at it that way. And a thiol contains an SH group. We also call those sulfhydryl groups. Thiols, if you think about where sulfur is in the periodic table, it's right below oxygen. It's in group 6A. It's going to have some similarities in chemistry to oxygen. Some. A lot of differences as well. But a thiol is essentially a sulfur analog of an alcohol. And there are such things as thiophenols. Ethers now, they contain, now look at the alcohol, it's an alkyl group, or some organic group attached to hydroxyl. Now with an ether, you have an alkyl group attached, single bonded to an oxygen, and then single bonded to another carbon atom. And the carbons have they're organic, they're alkyl groups. Okay, they don't have oxygens on it. So you can have, could be two CH3s in that slide. We're going to write the IUPAC names and common names for alcohols, phenols, and thiols, and some common names for ethers. We're going to learn to draw their structures and or line angle formulas as we've been doing. So we're not going to be doing anything really extreme, but we're going to be covering some ground here. and maybe I can throw hopefully some relevant things in there. So here we have what we're really going to be trying to do. So you have ball and stick models. They leave out the space filling models. Condensed formulas, line angle formulas, and then names. You see how those things look there. There's methanol, phenol, ethane, thiol, dimethyl ether. So that's identify the functional groups. Okay, aliphatic or an alkyl group. Aliphatic is why don't I get the let me get the whiteboard up here. I'm going to give you these terms because it makes it a little easier to talk about. You've seen aromatic. Okay, you've seen the term aromatic. It means it has this structure. Let me try that again. Okay. Nope, that's not working either. I'm going to stop this thing and I'm going to get it drawn right, and then I'll be back. Okay, there you have the 6-membered ring, the alternating single and double bonds. And of course there, it's in equilibrium with the other form. It would be like that. There's a concept called resonance, which we don't really, resonance, which we don't talk about here, but that double-headed arrow is typically used for resonance structures, where you have essentially benzene is an average of these two, a hybrid of these two, and you see that's why we put that little circle in there. So an aromatic ring has that in it, has that feature, and an aliphatic it's not aromatic. Okay, so aliphatic compounds, I mean, methane, okay, alkanes, alkenes, and alkynes are aliphatic. It comes from a word for it comes from some, I don't know, Latin or Greek word for fatty or something like that. And there's one other one that you'll see. I'm not going to use this too much. I will use aliphatic a lot. Alicyclic is the word I want here. And that is basically the cycloalkanes, cycloalkenes, cycloalkenes, and so forth, all right, etc. That's what I mean. So just remember, when I say aliphatic, I'm saying it's not aromatic. So here, aliphatic, for your purposes, equals not aromatic. Okay, that's all it means. All right. That way, I can use that word, and you don't really need to. You'll understand it rather than non-aromatic. It's I could say non-aromatic, but I probably will do that too. But so you know what that is. It's really, but that's all it really means. Okay, so these are all very important. These are all very important compounds, and there's a lot of these. You see a lot of these functional groups, and a lot of times you're going to see a lot of compounds that have functional groups of alcohols and aldehydes, for example. And I'll go right. I'll tell you right off the bat, the glucose, which is a 6-carbon sugar, which is your main energy source. It's both an alcohol and an aldehyde. Actually, it has several alcohol groups on it, hydroxyl groups. fatty acids. Okay, oleic acid is a carboxylic acid, and we haven't got there yet. We're going to get there next section, or well, in a couple of. In this lecture, we're going to get there. Carboxylic acid, oleic acid is a carboxylic acid, and it is an alkene. You're going to see these various functional groups showing up on the same molecule. You're going to find carboxylic. When we get the citric acid cycle, you're going to find there's going to be ketones and carboxylic acids, alkenes and carboxylic acids, and all kinds of combinations of these things. So don't get too overwhelmed. If you just take it one step at a time, this does get understandable, believe it or not, and you'll just be patient and you'll get there. Okay, now naming these things, we aren't really introducing any new concepts other than we're naming alcohols now, so we need another suffix. Okay, so we, rather than replacing it with ene or ine, now we're going to replace the e of the alkane with ol, all. So the common names use the name of the alkyl group followed by the alcohol. So you have methane, the OH there is methanol. The ethane, that's going to be ethyl alcohol or ethanol. All right. Remember there's ethene and ethine, and you see that you're using all the same basic names. You're changing the endings, or you're making some kind of, or you're specifying where on a molecule a particular substituent shows up, and you do it so as to keep the minimum number of the numbers that are specifying positions to minimum. And then, of course, you have certain features that define this as an acid or an alkene or whatever. But we're not really deviating from the system here. So let's give the IUPAC name for the following compound. All right. Well, it's obviously an alcohol, and we need to know, well, how many, what kind of alcohol? Okay, let's just look at this here. You see it's an alcohol. The OH is going to be something, it's going to end up in, let me do this. Okay, where we are now, you have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It's the longest continuous chain is 6 carbons. Okay, don't worry about what carbon atom the OH group is on right now. You just find a longest chain containing that group. So there's 6. So we have OH, and there's 6 carbons. So that means that, what do we have? Let's take a look at this. I told you to clear. There we go. We're talking about 6 carbons. Thing isn't back. Okay. We have C6. It's a C6 alcohol. I don't see any double bonds there, so it's going to be anol. It's going to be hexanol. All right, and we go back here. We look at the hydroxyl. The hydroxyl in an alcohol, the hydroxyl is going to give you it's going to specify, you're going to give the OH, the hydroxyl is going to have the lowest number, and you see it's the second carbon in, so it's going to be a 2-hexanol when we actually get this. So we're going to take, it's going to be something 2-hexanol, and I'd better do something here first. There we go. Okay, it's going to be a 2-hexanol. What's left? There's a methyl group there. What carbon is that? Well, we said the hydroxyl, it gets the lowest possible number because this is an alcohol. And So this is number 2 and 3, 4, 5. So it's going to be 5-methyl-2-hexanol. So 5-methyl-2-hexanol. 5-methyl-2-hexanol. That's what I get. What do they get? Okay, 6-carbon chain hydroxyl methyl group. Okay, so that's position of methyl hydroxyl, position of methyl and hydroxyl groups. You got to connect, replace E in alkane with all. Okay, so you name the longest carbon chain attached to the OH group by replacing the E in the corresponding alcohol name. So it's a hexanol, as we said. And number the chain starting at the end near to the OH group, which is 2-hexanol. Remember when we did that with the alkenes and alkynes? You number the chain to get that functional group the lowest number. Okay, so then they already give you the 5 there on that. So it's going to be 5-methyl-2-hexanol. So give the IUPAC name of the following 2 compounds. Well, I got a feeling there's some error in that one, but that is you notice that 1-methyl group is a little bit off of where it should be. But considering that you have, it's an awful lot like the previous one, but it's only 5 carbons. So 5 carbons instead of 6. So you could probably see right now it's going to be 4-methyl-2-pentanol. 2, 3, 4, 5. Yeah, 4-methyl-2-pentanol. Think about that. Just by analogy with the previous one, it's a 2-pentanol because the hydroxyl is on the 2nd carbon. In fact, the hydroxyl defines that carbon as the 2nd carbon because you give the hydroxyl the lowest number. What about the other one? Well, that's a phenol. Phenol, remember, the substituent on phenol, toluene, there was another one, aniline. You're going to see benzoic acid. That pretty much specifies the 1 carbon. So the hydroxyl gives the 1 carbon because that's a phenol. So it's 3-bromophenol. Just look at the numbering. The hydroxyl group is on the 1 carbon, and then the lowest number is going to be 3. You go all the way the other way around, it's going to be 5, and you're supposed to give things the lowest number. And we'll go through that. And okay, we're going to put these things together. The pentanol, phenol. Okay, 2-pentanol, phenol, 4-methyl-2-pentanol. Pretty sure that's what I said. And 3-bromophenol is how that's going to work. And a little bit of applied chemistry here. I mentioned glucose. Glucose is a 6-carbon sugar. And if you draw the structure of it, sugars have a basic structure that gives you hydroxyl groups and then either an aldehyde or ketone group. But they actually, in practice, they exist in a cyclic form. But we won't worry about that now. The glucose, just drawn out, is going to have 5 hydroxyl groups and 1 aldehyde group. Okay, so it's an aldehyde and a sugar, or an aldehyde and an alcohol. And it undergoes fermentation to ethanol and carbon dioxide. That's how the yeast molecules that generate alcohol, and I guess there's a few other, I think, organisms that do that, but definitely yeast. It actually uses the glucose for energy. Okay, this is, you go to ethanol and now you're giving off CO2. You're burning the glucose to ethanol and carbon dioxide. And glucose, of course, is our main fuel. You burn it to just carbon dioxide and water. But that's one place where you find alcohols in biochemistry. And they talk about how it's made. Industrial, it's going to be, you can make it by fermentation, fermentation. Obviously, you ferment grapes, you get wine. You ferment grain, you get beer, and you can ferment a lot of things to get alcoholic. Ferment potatoes, you get vodka, and you distill vodka. Actually, you ferment grain, you can get beer, but if you distill it, you get whiskey. You distill what you get from fermenting potatoes. You distill that, you get vodka, and wine. It's brandy. Wine goes to brandy and so forth, stuff like that. But anyway, it's really doing that on a massive scale is a little difficult. So what you usually do is you take ethene, and you react it under pressure with water, high temperatures, pressures, and you'll get ethyl alcohol. Of course, that ethyl alcohol is, you usually don't want to consume that. You want alcoholic beverages, you want it from fermented sources, because these things are going to have side products that aren't particularly too good for you. And too much alcohol is not too good for you either. But 1,3-propane triol is another alcohol. This is called glycerin. Do they say that here? They don't say that here, but that is a trihydroxy alcohol. Oh, they do say glycerol. You'll see glycerin instead of OL. You see INE sometimes, and that is a component in fatty acids, or in fats and oils. There's 3 hydroxyl groups, and that particular material is very polar, very soluble in water, and they point out it's used as a skin softener and skin lotions, cosmetics, shaving creams, liquid soaps, and glycerol. The GLYC comes from glucose or something like that, which is a Greek word for meaning sweet, maybe means sugar, something like that. And I don't believe glycerol is particularly toxic. Of course, it really couldn't be, because fats get broken down during metabolism to give you the fatty acids and glycerol. But it's that is an alcohol. It's a trihydroxy alcohol, or a triol, you could say. Ethylene glycol. Here's one this is one that has some health risks to it. It's used in antifreezes in heating and cooling systems. It's probably going to be used in car antifreeze, and as a solvent, and in the production of some synthetic fibers. It has a sweet taste, and I hope you've never tasted it. It's very bad for you. It gets oxidized to oxalic acid, which form insoluble salts in the kidneys that cause renal damage, and actually it's that type of situation is extremely painful. So you need to be careful with ethylene glycol. There are some antifreezes now that use, I believe it's propylene glycol, which isn't quite as bad, and to avoid use of ethylene glycol. But there's still a lot of ethylene glycol around, and you need to be really careful of this stuff. It's really bad stuff to get inside you. Bisphenol A is, we're not going to go into the details of this, the naming completely. I'm not going to go into any great detail. I will say that bis, it looks like bi, BI. Well, bis is related to that. So bis is like 2 of something. So bisphenol, there's 2 phenol groups, and you see the 2 phenol groups on that molecule. So it's an alcohol. It's an aromatic alcohol, the phenol, and that's used in a lot of plastics. You make polycarbonate with it. You wash. You can, depending on, if you put this in a dishwasher and use the wrong detergent, you can break it down so you can get BPA, which is also has some bad health and environmental effects. So that needs to be, polycarbonates need to be treated with some care. There's a few other things. Phenols show up in a lot of essential oils of plants. Well, alcohols show up in a lot of essential oils of plants too, and also in other natural products. Phenols are uh, they're aromatic. They're aromatic compounds. We've talked about that aromatic ring, the benzene ring, and they tend to be uh, have very nice smells. And you see a few there. Vanillin, we saw that before. Eugenol, thymol, probably from thyme, and isoeugenol. There's a lot of these. There are a lot of these things. A lot of spices, a lot of seasonings get their smell from these types of compounds. Thiols were, here's another interesting kind of compound, thiols. They contain sulfur. They contain a thiol group or a sulfhydryl group, we will call it. I'm going to go ahead and write this down so you see it. Let's erase this. With thiols, there's the SH. That's a thiol group. It's also called a sulfhydryl group. Just for completeness. And these are, if they look like if they look like they're analogous to hydroxyl group, it looks like it's analogous to a hydroxyl group. It is, because sulfur is in the same group as the periodic table. It's right under oxygen. But thiols are, there are thiols there's an amino acid, cysteine, which is a sulfhydryl group on it. And there's a few other things that you see sulfhydryls now and then in proteins. Well, it's in cysteine mostly. They have very strong and disagreeable odors most of the time. They mention, cheese, onions, garlic, and oysters. Okay, well, there's, the main odor from onions comes from, I don't think it's, I should have known this. I was a sulfur chemist, but it's not that itself is the odor from onions is a sulfur compound, but it's, thiols are found in onions. And it's actually a mixture of mercaptans. These are all called mercaptans as well. Thiols. Okay, thiol is also, you'll see mercaptans. It comes from mercury capture, stuff like that. They bind to mercury pretty well, real well. They have what they have in natural gas is a mixture of some mercaptans, methyl, methane thiol, ethane thiol, a couple of them, and they use a different one. They always use a different. They change these things once in a while, so that when you smell gas, which you're smelling a mercaptan or a mixture of mercaptans, you call these guys out and they're going to check it out, and they can figure out, they can kind of tell, well, yeah, that's the mixture we're putting in the lines right now. And so then you do have a problem, and then you find out it's something else, and well, you need to find out where it's from, because these things do have bad odors, and mercaptans do tend to be toxic, particularly aromatic mercaptans, or at least some of them. Okay, naming these things, same as we've done before. It's pretty much like naming an alcohol, except instead of you don't lop off the E from the methane for methane thiol. You just methane thiol, ethane thiol, as you see there, 2-butane thiol. But other than that, the sulfhydryl group, the thiol group, is the SH group, is given the lowest possible number, and then everything is named from there. So that's Anyway, they mentioned here Thiols family of sulfur-containing organic compounds that have a thiol group. So there they give you some place where some thiols come from. As I said, propane thiol is really not the one propane thiol they give it in onions, but it is not the main. Propane thiol really does not smell like onions. It's these things really do smell bad, but in very small amounts they'll affect the smell of something else, and it won't be. If you like the smell of onions, and I think the smell of onions, food being cooked is actually quite pleasant. So just know that there's some propane thiol in there. And then there's the smell of garlic, propene thiol. So ether, we're going to ethers now. You go back, let's take a look at alcohols and thiols. You see you've got an alkyl group and an OH or an SH. All right. You can replace that hydrogen on the OH or SH with something else, like another alkyl group. And when you do that, you get an ether, or a thioether, or a thioethers and sulfides are they're kind of used interchangeably. We're not going to worry. We're not doing too much with the chemistry of these. We're just giving you the names. So an ether contains an oxygen between two carbon groups that are alkyls or aromatic rings. Okay, we're going to see oxygen between two carbon groups that are other than alkyls or aromatic rings as well. So remember to distinguish ethers from those when we get there. They are analogous to water in ways. They have the bent structure, because if you draw the electron groups around oxygen, you're going to see there's 4 of them. And the electron geometry is going to be tetrahedral. And this is true for alcohols as well. And these things they tend to be polar. So the smaller ones are going to be soluble in water. We haven't really talked too much about water solubility in this group yet. But they have common names. We're only worried about common names. It's the names of the alkyl groups followed by ether. So you see dimethyl ether. Okay, that's fairly simple. There's diethyl ether. It's used as it used to be used as an anesthetic, general anesthetic. Maybe it still is. Then there's dimethyl ether. And to do the common name, you simply take the alkyl groups and write them one after another and say ether. Write them one after another in alphabetical order. And if there's 2 are the same, it's diethyl, dipropyl, dimethyl, something like that. So there's methyl in a propyl group. This is methylpropyl ether. There is, I mentioned it somewhere on these slides. I'm not quite sure where, but there is that propyl group there. You notice you might remember there's 2 propyl alcohols. There's one propanol. No, maybe we didn't talk about that. But there's 2 kinds of propyl groups. One with the 3 carbon chain with the attachment to whatever it's being attached to. In this case, the oxygen is at the end, and then another one you can have it at the. We have this here. We'll have. Okay, you can have a propyl group, and they don't really talk about this in what you're doing here, but I'm going to mention it anyway. This would be a 1 propyl, and then there's this could be either 2 propyl or isopropyl. Actually, it's isopropyl is the way this would be called. This really is not UPAC. So this isn't IUPAC. It's the IUPAC is really kind of a bizarre is a bizarre thing that even I never keep straight. But there's two of these things. So this is a propyl group. This one here. This is propyl, and this would be isopropyl. This is isopropyl alcohol. I think we saw that in. Oh, we are talking about alcohols. I'm pretty sure we saw that somewhere before. But anyway, this is methylpropyl ether. All right. And I already mentioned that some ethers are used as general anesthetics, and they block signals to the awareness centers of the brain, so you don't have any memory, you don't feel pain, and you have an artificial sleep there. And here's some of the ethers that are used in anesthetics, been used for hundreds of years. So hundreds of years until the 1950s, ether was. I don't think ether was used in anesthetics for hundreds of years. I think it's just started in the 1850s. But the 1950s, they got a new group. They had new groups of anesthetics, but they retained diethyl ether was used that way. They retained the ether group, and they replaced the hydrogen atoms on the carbon with halogen atoms to reduce the volatility, mostly reduce the flammability of the ethers, because those ethers are really pretty volatile to begin with, although that it does reduce the volatility of them. So these things are gases. The other ethers are liquids. They evaporate very readily, but these are much more useful in terms of their safety factors because they're a lot less flammable. So lastly, let's take a look at writing the structures for some of these things. 3-pentanol, ethanol, and diethyl ether. Let's look at 3-pentanol first. 3-pentanol, let's call it 3-pentanol. Doing that. Okay. 3-pentanol. When you have what IUPAC name, 3-pentanol, it's giving you all the structural information you need to write the structure. This 3-pentanol defines the structure of that molecule. Okay, you really, benzene doesn't really tell it. Well, you know what the structure of benzene is, and since we've set benzene as the standard basic aromatic ring, but without us defining it that way, it doesn't really tell you much about the structure, but you define it that way. Now you're given the structure. Vanillin. I mean, it tells you the structure, but you don't have vanillyl groups. But anyway, pentanol, 5-pentan. This is from pentane. It's obviously from pentane-all. Okay, so you have 5 carbons. First thing you look for, that's your longest chain is 5 carbons. You notice I'm writing backwards. You do that a lot in organic chemistry. Okay, so then you have an all, 3-pentanol. So there's going to be a 3, it's going to be on the 3 carbons. So we go, well, if you go from left to right, it's 1, 2, 3, and it's here. And if you go from right to left, it's 1, 2, 3, and it's here. So the hydroxyl group is there. So you're going to write this, now you fill in the, you fill in all the hydrogens. And if you want to do the line angle formula, you'd write it like this. Okay. You do something like that. And that's really how you go about writing these things. You just, draw the carbon skeleton and fill in the the functional group, the substituents, and then all the hydrogens and so forth. Diethyl ether, well, we already saw that, right? Diethyl ether is simply, it's an ether, diethyl ether. So you know that it's that. And ethyl, you know, is CH3, CH2. Remember those functional groups. So there's CH2 there. It's going to look like that. You just take it a step at a time. You know, first thing is, you know, see what all the pieces you're given. The pieces you're given with is the pentane and all. And then they tell you, okay, you've got a 5-carbon chain. It's under 3 carbons, so you've got that in ethanol. You know, it's got to be 2 carbons and so forth. So there's the structures. I didn't write the ethanol there, but you should have known that from what we've seen so far. So that's 12.1. Now we're going to go on to 12.2, and then 12.3, and then we're going to have to get into chapter 14. Okay, when I finished up the previous lecture, I was somehow I felt like I was already on section 12.2. Well, I did say 12.2 and 12.3, but I got confused because of what was actually in front of me. But we have 12.2, properties of alcohols, and this is actually going to be very short. There's properties of alcohols are, you know, well, let's just talk about them. Alcohols, well, when you put a functional group on a hydrocarbon, like you're putting an alcohol on ethane to make it ethanol, or ethanol, yeah, you're going to get very different properties. And one of the things, ethanol is a good in hand sanitizers. Alcohols, however, are flammable, so these things are fire hazards. So you do need to be careful with them. And we're going to also talk about classifying alcohols, and we're going to describe their solubility in water. So that's really what this is going to be about. You have 3 different kinds of alcohols. You have primary, secondary, and tertiary. And primary, secondary, and tertiary are determined by how many carbon atoms, or how many alkyl groups, how many carbon atoms are attached to the carbon that has the OH group. Okay, so look carefully at these 3 these 3 structures. Okay, there's 2, and there's that 2-propanol. I knew we saw isopropyl alcohol somewhere. That 2-propanol is also known as isopropyl alcohol. That's what's in rubbing alcohol. But you can see that it's a 3-carbon chain with a hydroxyl on the 2nd carbon. So when we go to ethanol, you look, there's a hydroxyl, OH. It's attached to a carbon, and that carbon has one other carbon attached to it, a methyl group. That's ethanol. That is a primary alcohol. A secondary alcohol, you start at the hydroxyl group, you go to the carbon that it's attached to, and how many carbons are attached to the hydroxyl group. All right, that's a secondary alcohol. Tertiary alcohol, there's 3 carbons attached to it. So 2-methyl-2-propanol is a tertiary alcohol. These things have different properties. We're not going to really go into them, but ethanol and 2-propanol, ethanol is very different from 2-propanol. They do different things, okay? There's certain reactions, there's certain chemical reactions that each one will distinguish each one from the others. One example would be if you were to heat up ethanol with sulfuric acid, you would end up getting diethyl ether. That'd be the main product. 2-propanol, you'd probably get some ether. You'd probably get some di-2-propyl ether, but you'd also get some propene. And if you did it with 2-methyl-2-propanol with sulfuric acid, you'd get ethylene, or you get it's called isobutylene. It's an alkene, but that would be 2-methylpropene. That'd be 2-methylpropene is what you'd be getting. So they do different chemistry. So let's quickly quiz. A quick quiz about what are these, primary, secondary, or tertiary? Okay, well, remember, the definition, or what the determining factor is how many carbons are attached to the carbon bearing the hydroxyl. And in A, there's 2, so that makes it secondary. In B, it's 1, that makes it primary. And in C, it's 3, so that makes it tertiary. So it's going to be secondary, primary, tertiary. So it's going to work, secondary, primary, tertiary, you see. Another thing with alcohols, and we're getting into, with alcohols now, we're getting into, remember, this is the first time we're looking at something other than hydrocarbons. We're looking at something that's got substituents that have oxygen on them, that have, oxygen for the most part. We're going to be talking about amines shortly, but there's oxygen, there's hydroxyl groups. They're very polar. They form hydrogen bonds. Remember that we talked about hydrogen bonding. That's why I had you to go through those two, the 1 or 2 sections where they talked about these things. You see the hydrogen bonds. So these things are going to be soluble in water if they're not too large. And if they have 1 to 3 carbons, they're soluble in water. When you get up to 4 carbons and more, the solubility starts dropping off. So something with ethanol, ethyl alcohol, you can buy, alcoholic beverages are solutions of alcohol and water, and of course other flavorings, and so other things as well. And soluble in water. Isopropyl alcohol, rubbing alcohol, that's 2-propanol. If you're naming it with the IUPAC name, that's 70%, I believe, 70% isopropyl alcohol. So there's, they're soluble. You get into the butanols, and then the solubility starts dropping. There's going to be a little bit of solubility there. So when you get up into this one, the one they give you there, that's a 3,8, that's the 3,6,8. That's 1-octanol. If you're sharp enough to spot that, that's insoluble. That's what happens is you have a polar, very polar group, or the methanol, methanol, ethanol, propanol. They have the hydroxyl group is the polarity of the hydroxyl group is enough to overwhelm the hydrophobicity, the lack of polarity, the non-polarity of the alkyl group. And then when you get bigger and bigger, you're really diluting that effect of the hydroxyl. So it gets less soluble. So these are the properties we're really worried about. We're not worried about, but we're focusing on the solubility in water. Some of these things, the smaller, lower molecular weight ones are soluble in water, and then you get up a little higher, and then they're not soluble in anymore. And here you have, there's a list of the solubility of some alcohols, and this is in your text. This is table 12.1. Okay. These things use hand sanitizers, a chemistry linked to health. Okay, they're used as an alternative to washing hands. They kill bacteria and viruses. They're toxic. Alcohols are toxic, and actually, phenols are actually quite good antiseptics. And you see one given there in a slide. They are these alcohols, they are highly flammable. Ethanol boils at, I think, 78 Celsius, which is, it's more volatile than water. You can ignite it fairly easily. And most of these, if you're under 8 carbons with most of these compounds, you need to be careful with them because they do burn. Phenols, well, they have 6 carbons. So already there's 6 carbon. That's quite a bit of carbon on it. That's quite a bit of organic on this stuff. But they're slightly soluble in water, and because of the fact that they have a hydroxyl group that can form hydrogen bonds with water, so they can react with water to produce phenoxide ions. Used to be used as antiseptics, and there's old books on medicinal chemistry that talk about the antiseptic properties of the not only phenols, but alcohols as well. And they're better and better at sanitizers or antiseptics as they get smaller and smaller. Of course, they become more toxic, and they also can do more damage to the skin and so forth. So there's a lot of old literature on these things. All right. Whether each of the following is soluble in water, and explain why. Well, the first one, let's look at the second one first. CH3CH2OH. Well, that's ethanol, and that's soluble in water. Why is it soluble in water? Because you have the hydroxyl group is 2 carbons. It is 3 or less carbons, and then this one is 1 hexanol, and that's going to be insoluble. And so why is one soluble and the other is not? Well, one's a long chain alcohol, the other's a short chain alcohol. Alcohols with long chains are nonpolar and are not soluble. Short chain alcohols form hydrogen bonds with water. Actually, anything with a hydroxyl group forms hydrogen bonds with water, but it's just not. It's that long chain. Just it's going to essentially. Well, it's going to prevent the alcohol from forming hydrogen bonds, because it's actually not going to let it go into solution with the water. So it'll be something like that. Okay, so that's section 12.2. Talked a little bit about properties. We talked about primary, secondary, and tertiary. We talked about solubility, and that's talking about their role as antiseptics. You can use them to kill bacteria. They work as antiseptics, but they're very broad spectrum. They're not specific to bacteria. They can kill other organisms, other small organisms. So, but that's section 12.2. We go on to section 12.3, and then we'll be done with chapter 12. This is section 12.3. It's aldehydes and ketones. Now we are moving to another kind of functional group. We had alcohols, thiols, and ethers. They were carbon singly bonded to carbon, and alcohols with sulfur, also oxygen and carbon singly bonded to sulfur. We're not going to be taught. There are sulfur analogs of these things here, but we're not going to worry about them here. They really don't have a lot of biological significance that I know of, and they don't talk about them in the text. Simplest ketone is called acetone or propanone. It's propanone. How many carbons does it have? 3. These things can be solvents. Well, acetone is in nail polish, and nail polish removers, some paints, cleaning fluids, rubber, cement, and various other things. It's a pretty good solvent. It's fairly polar, not as polar as an alcohol, but it's still polar. And we're going to just talk about their formulas and then describe their solubility, which is, by now, after the talk we've had about alcohols and alcohols, phenols, and ethers, you're going to realize that you probably should anticipate that it's going to be similar, and it is. We're going to get into the chemistry first, the structure, and the defining structural feature of aldehydes and ketones is the carbonyl group. The carbonyl group consists of a carbon-oxygen double bond. Carbon-oxygen double bond is polar. Remember the difference in electronegativities, the electronegativity thing. That's going to be a very important factor here. You have a carbon which is attached, which is not real electronegativity. It's sort of in the middle. And then you've got oxygen, which is very electronegative. So you have a very strong polarity there. And The oxygen has two lone pairs, very strong bond dipole, partial positive charge on carbon and a partial negative charge on oxygen. So that defines the chemistry. You will, from what you learned, if you did go through those last few sections of the, I forget which chapter it was, but it was the one on the chemical bonding, some of the electronic structure and the electronegativity and so forth, and the different types of non-bonding interactions, hydrogen bonding, dipole interactions, and so forth. You might be able to maybe kind of guess at some of the chemistry and some of what they do. But anyway, that's the basics of a carbonyl group. We have here, okay. A carbonyl group in an aldehyde has one alkyl group and at least one hydrogen atom, because there's something called formaldehyde, which is not there. Formaldehyde is an aldehyde, but it doesn't have any alkyl group. So if you look at the aldehyde in this slide, you see the one H, the one with the H. If you replace that, the methyl group, you replace the methyl group with a hydrogen, you have formaldehyde. Okay, so that's this. The carbonyl with a hydrogen group is an aldehyde. Ketone, it has two alkyl groups, always. We write the aldehyde group as CHO, and the double bond is understood. That happens quite a bit, where we have a double bond and we write that group in such a way that we just understand that the double bond is there. These are a lot of what we're doing here is, well, a simple example where we don't use a subscript of 1. Methane is CH4, and not C1H4, CH4. C1H4 is wrong. You don't need it. And the ketone group, the keto group, which is the carbon, essentially a carbonyl, and you've got two carbons attached there. You can sometimes write it as CO, so you'll see it written those ways, and that will, that makes writing it a little easier. If you're typing something out, it's kind of hard to type the double bond. So you'll use this CHO and CO. Naming them, not much different from what we've seen so far. You're going to be safe from having to deal with other substituents on that carbon with the double bond, because you're going to have the other valences are going to be taken up. So a little bit of simplification there. The common names, there's IUPAC name is just you take the alkane name. When aldehyde, you take the alkane name and you change it to Al. It's going to be on the end carbon. So, it's going to be propanal, propanal, ethanal, butanal. I mean, there's no 2-butanal, there's no 2-propanal, there's no such thing. All right, because the aldehyde is going to be at the end of the chain. So that should make it a little easier. So one carbon in the common names, there's from formaldehyde. And I mentioned formaldehyde. I said formaldehyde, but you could call that methanal. That would be the IUPAC name. And there's two carbons from acetic acid. Acetic acid is, remember, acetic acid, ethanoic acid, or acetic acid. So it's two carbons, so it's acetaldehyde. 3 carbons of propion, aldehyde. You don't see that propion too often. We're going to see carboxylic acids. You're going to see propanoic acid. You do see propionic acid, and then 4 carbons butyr for butyraldehyde, and they're all followed. You see, they're all followed, but you've got the common name of something from a common name, and then some prefix from the common name, and then you add aldehyde to it. That's what you're seeing there. So let's take a look at some of these things. It's all, like I said, it's all going to be at the end of the chain. So from that standpoint, the aldehyde's the one carbon. So methanol, ethanol, propanol, butanol, or formaldehyde, acetaldehyde, propanaldehyde, butyraldehyde. It's reasonably simple. You pretty much need to know these things because you'll see both of them. In practice, you're going to see both of these names. In fact, you'll see the common names more often, but you do need to know the IUPAC names, and of course the IUPAC names are much more descriptive than the common names. So let's name this thing. It's an aldehyde. And you really, if you look at this thing, it should be pretty simple to work out because you know that the aldehyde group is going to be the one carbon because it's at the end. And you just count carbons until you get to the substituent, and then you're there. So this is, you look at it, how many carbon atoms in the longest chain you have a couple choices here. All right, this is essentially a branched chain, but you have the one with 5 carbons, and then you've got another one. If you go to the number 2 carbon and you go down, there's a 3 carbon chain there. Well, you take the longest chain, and 5 is pentanal, so it's a pentanal. And since the aldehyde is the one carbon, the methyl is on the 2nd carbon, so it's 2-methylpentanal. You don't even have to put the number on the aldehyde. So it's a pentanal and 2-methylpentanal. That's it. That's how you do that. Now, naming in ketones, we get a little bit more. We need to think about these a little bit more, but not too much. Same rules. You have a chain with the ketone in it, and you see what we have. There's propanone, butanone, 3-pentanone. Now we got to start numbering these things because if you see with propanone, there's only one possible propanone. 4 carbons, butanone. Okay, if you see that you have the carbonyl group on the 2nd carbon from the end, what if you moved it over to the one to the left of it? Well, now the end it's still 2nd from the end because the other carbon is going to be the one carbon. So pentanone, there's going to be 2 pentanones, a 2-pentanone and a 3-pentanone. Okay, and I want you to listen to this and think about what I'm saying. And in fact, I'm going to draw the pentanones here. I told this thing to clear. Okay, I'm just going to draw the carbon skeleton here. You can fill in the 4, 5. You can fill in the hydrogens and so forth. Okay, they gave you a 3-pentanone. Okay, that's 3-pentanone. Hope you can see that. But I could as well put the carbonyl group here. Boy, it's hard doing this when you can't, it's hard writing on this whiteboard when you can't see what you're writing, when you're writing in one place and looking at another. But anyway, okay, that's going to be 2-pentanol. Now, if it's let's just take a look at this for fun. Let's take a look at a hexanone and see what happens there. 1, 2, 3, 4, 5, 6. Okay, so we're going to have these hexanones. Okay. Well, we see we have 2 pentanones. There's 2 pentanones. How many hexanones are there? Well, we could put one here. That would be 2 hexanone. We can put one here. That'd be 3-hexanone. And well, if we put one here, that's going to be 3-hexanone because we would count from this end. So there's only 2 hexanones. There's 2 hexanones. If you go to the heptanones, and let's just do that. Let's just do that for. Okay, so remember the N carbons put it on the N carbon makes it an aldehyde. So there's only going to be one pentanal. There's only going to be one hexanal. There's only going to be one heptanal. And anyway, we're going to the heptanones. And I know you're very busy studying for these things, but one thing that you can keep in mind is that what I'm doing here is I'm lecturing and I'm also thinking out loud at the same time. I'm working problems. I go, what if? So, you play around with these things a little bit. You say, okay, draw a different structure. Well, how would you name it? How many of these things would there be? So how many heptanones would there be? Is it okay? Because you've got these numbering. It gives you practice with the chains, numbering, so forth. Okay, so we could put it here, and that's going to be 2-heptanone. Okay, we can put it here. That's going to be 3-heptanone. We can put it here. That's going to be 4-heptanone. Now, okay, this is 1, 2, 3, 4, and we can number it this way. We number 1, 2, 3, 4 here. So there's going to be a total of 3 heptanones. And then as you get longer and longer chains, you're going to get more combinations of these things. Okay, so let's go back to here. So there's the straight chain. I'm going to keep using straight chain. I think you should know what it means. Okay, fine with the non-cyclic ones. Now we need to go to the cyclic ones, but we really aren't going to change much. The common name, with a common name, the alkyl groups attached to the carbonyl group are named alphabetically. I missed that, but then you could take C double bond O is ketone, and then you just add the names of the substituents in alphabetical order. So dimethyl ketone or acetone, ethyl methyl ketone. Note that ethyl is the alphabetically the first, and then there's diethyl ketone. Okay, you do that. Now you get into the cyclics. It's a similar thing. The ketone is going to define now. This is a little tricky now because the ketone itself, the position of the ketones now is the 1 carbon in cyclics. So keep that in mind. Okay, there's. Let's just take a look at this. Okay, if you have a open chain, you have, what do you have here? You've got C, 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 C. Okay, you put this here. This is, okay, it's a 5 carbon. This is going to be the 2 carbon. All right. You're never going to have an open chain ketone where the keto group is on the 1 carbon. Actually, that's not true. You could have, if you haven't, well, there are some circumstances where you could, but usually you won't. In the case of, I doubt if you're going to see any of those in this course, but if you have this, no, I don't want that in there. I don't want the circle. This is cyclohexanone. Okay, cyclohexanone. This is the 1 carbon. So this would be 2-methyl cyclohexanone. This, and you have that. This would be 3-methyl cyclohexanone. This would be 4-methyl cyclohexanone. This, what I have written here, is 3,4-dimethyl cyclohexanone. Okay, so you're going to have a little bit different numbering now when you get into the cyclic ketones, but that's 3-methyl cyclohexanone. So let's name one or two of these. You have named the following ketones using the IUPAC system. Well, that's a 5-carbon chain with the keto group is the second from one end, so it's the 2-carbon. So it's going to have to be 4-methyl 2-pentanone, right? 4-methyl 2-pentanone. You're going to have to give the number of where the ketone is. Okay, it's not like aldehydes where you could just say 4-methyl pentanal because there's only one pentanal. So it's pentanone, and you get 4-methyl 2-pentanone. Okay, 4-methyl 2-pentanone, right? Now, now we've done so much for the nomenclature. You get in a water solution. Aldehydes and ketones can form hydrogen bonds with water molecules. Remember, the alcohols can form hydrogen bonds from either end. They can form a hydrogen bond from an OH, the hydrogen of the hydroxyl group, hydrogen bonding with the oxygen and water. Aldehydes and ketones can't do that because they don't have an OH bond, but they can still hydrogen bond to water molecules. So 4 or fewer carbons, they're going to be soluble. When they have longer chains, which are not chains are nonpolar, that they're going to diminish. They're essentially reducing. And here's what's going on: the longer chains are diminishing the effect. They're diluting the effect of the carbonyl group. You have more hydrocarbon and less hydroxyl, or more hydrocarbon and less keto, and that kind of thing. So here you have a list. There's you have butanone and down to methanol. They're pretty soluble in water. Pentanal and pentanone slightly soluble, and then hexanal and hexanone are effectively insoluble. There's a few of these things that are important. Acetone is used in nail polish remover, cleaning fluids, and paint. Formaldehyde is used in biological specimens. Formaldehyde, by the way, is a gas. So when you see like the jar, that preserved specimen there, that's in a solution of formaldehyde in water, which they sometimes call formalin. You'll probably see that in some of your maybe comparative anatomy lab. You'll probably hear about that. Some other ones: benzaldehyde is in almonds. Vanillin, that's an aldehyde. And cinnamaldehyde, which is responsible for the smell and sometimes taste of cinnamon. And let's just do this classification here. And we're getting close to the end. We have aldehydes or ketones. Which are they? Well, remember, the aldehyde has a carbonyl with at least one hydrogen attached. So look for those. You can see 2 of them. A ketone has carbons on either side of the carbonyl group or keto group, and there's 2 of those. So you should see that A is a ketone, D is a ketone. It's a cyclic ketone, to be exact. B and C are aldehydes. It doesn't really matter what other decorations there are elsewhere. The C double bond O, the C, the carbonyl with a hydrogen attached to carbon, that's an aldehyde. So it's going to be A and D are going to be ketones, and B and C are going to be aldehydes. As you see, they are. Now give the IUPAC name of these. There's plenty of other practice in your text, so I'm going to do these. You can probably, the first one, the IUPAC, you would pick it's a ketone. Okay, so you take the chain. There's no substituents. There's no branching, so it's just a 6-carbon chain. So it's a it's a hexanone, and it's the second carbon in, so it's 2-hexanone. And here on this one, well, let's go back to the start. It's we're talking about B here. It is you would call it a butanone, but the way they name it, they give the correct name for this thing, but the way you're told to name these things, you might be tempted to call this 4-methyl butanone, because the carbon atom is going to give you the number of the carbon chain. But what they do is they give you, okay, let's go on. You're going to see this is 4-chloro-2-butanone, and this particular nomenclature is, you would think, well, you don't need the 2 in the butanone, but you do need the 2 in the butanone. And something I said earlier on, and this is, I know the text didn't really explain this, and it's really gets into kind of more complicated chemistry, some more complications of chemistry, just to show you. I did mention a little while back that you can have a 1-something-one. Okay, so you have. Let's look at, if you just say the compound butanone. I mean, that's butanone. It's unsubstituted. There's no doubt where the carbon-carbon double bond is. But when you have a substituted butanone, now you get another issue here. If you take, and here's one that I actually looked this up to make sure. Okay, that's a phenyl. That's well, we call this a phenyl group, but I'm just going to draw this thing. That one is 1-phenyl, 1-butanone. And then if you draw, okay, just put this thing up here. And this is really an aside. This is not something you're responsible for. I just wanted to just to explain this. You do this. Now you have 1-phenyl, 2-butanone. Something like that. So when you have substituents on, if you have substituents on the bottom line, let's go back to here. If you have, okay, this is just butanone. You could write this as butanone. And by the way, if somebody asks you to draw that or name that and you say butanone and you get it marked wrong, let me know. And if you say 2-butanone and you get it marked wrong, let me know, because you can see these things. I have a handbook of chemistry and physics here, and they give this as 2-butanone. And I know your text gives it as simply butanone. And then, but you put a substituent here. When you put substituents on it, then you want to give the names of the of the butanone. See, 4-chloro-2-butanone, something like that. I know that's not a good explanation, and it was really, I think this example might be a little bit beyond what's really the scope of this course, but yeah, this is 4-chloro-2-butanone. In 4-chloro, and okay, if you're asked to put this down on a homework, and something like that on a homework, and I'm probably going to get a lot of questions about this, but let me know if these things get marked wrong, because just to be honest, chemical nomenclature, organic nomenclature is a very complicated subject, and there are whole books on it. There are people who actually study it. Okay, so there's going to be ambiguities. There's very few chemists that have it down completely. I've only known one in my life who really understood nomenclature perfectly, and he's probably, you could probably number those on, there's probably no more than a dozen or two of them that really know this in detail. So that one, I think it was a little bit, for this course, that was probably not quite the right example to give. But anyway, I'm enough of that. But they give 4-chloro-2-butanone, and that's hopefully that won't cause any problems. Usually, if you put the numbers down, even if it's redundant, it's correct. So, and that's about all I could say about that. Okay, we got to move on. I got to get to chapter 14, and I want to get this thing done today. So, if you have any questions, let me know.